Good afternoon. My name is Neil Kidner with NetService. Today I would like to share with you an update on our project that NetService has been leading, titled Cobalt-Free Cathodes for Next Generation Lithium-ion Batteries. We are currently approaching the midpoint of our project. An overview is provided on this slide. The key barriers the project addresses are improving cycle life to greater than 1,000 cycles with less than 20% energy fade, and reducing costs to enable an overall cost of less than $1,000 per kilowatt hour. NetService is extremely fortunate to be partnered on this endeavor with Ohio State University and Navitas Systems. Led by Dr. John Won Kim, the OSU team are working on cell chemistry development and battery testing, and Navitas are bringing their extensive manufacturing expertise for large-scale electrode fabrication and the manufacture and testing of 2 amp-hour cells. Driven by the anticipated growth of electric vehicles and the resulting demand for battery materials, concerns over the security and availability of critical raw materials has renewed interest in reduced or no cobalt battery formulations. This provides an opportunity to strengthen the US supply chain and manufacturing base and re-establish US dominance in the battery market. Our project centers around demonstrating the viability of a cobalt-free titanium-substituted LMNO high-voltage cathode. Poor cycle life has limited its adoption. The objective of this project is to identify both novel microstructures and cell chemistries to improve stability and low-cost, scalable manufacturing processes. Our concept and approach is shown schematically on this slide. Leveraging synthesis techniques NetService has developed for fuel cell and catalyst applications, we are working to develop new core shell microstructures to preferentially locate titanium at the surface of the cathode. When coupled with new cell chemistries, our goal is to stabilize the high voltage system. 2019 culminated with the demonstration through 2 amp-hour cell testing of the potential of our concept to provide a meaningful improvement in cycle life compared to the LMNO baseline. As shown on this slide, the project has a structured roadmap to systematically improve cell performance and achieve the project goals. Over the next 5 slides, I'd like to share with you some of the key accomplishments the team has achieved over the last year. In year 1, an important goal for NetService was to scale a solid-state synthesis process to manufacture the LMNTO powder to support cell development. The solid-state process was successfully scaled from 20 grams to a 2 kilogram batch size. The roadmap has been identified to scale to larger batch sizes in the future as appropriate. In parallel, for the implementation of several process improvements, the homogeneity of the solid-state powder was increased from 87 to 94%. The Ohio State team has led a significant effort to identify optimal cell chemistries that are compatible with the high-voltage LMNTO cathode. Building out single-layer pouch cell fabrication and testing capabilities has allowed a wide range of alternative binder and electrolyte additives to be quickly evaluated. This slide shows the voltage versus discharge capacity curves and cycle life behavior for single-layer pouch cells with the down-selected Project Progress cell chemistry. This chemistry incorporates an LiPAA electrode binder and a LiBob electrolyte additive. A campaign of 2 amp-hour cells with the down-select chemistry have been manufactured by Navitas for the Year 1 Project Progress deliverables and for internal testing. In addition to the down-select LMNTO cell chemistry, additional 2 amp-hour cells were manufactured with LMNO cathodes and without the advanced binder and electrolyte additive to help us better understand the effect of the different cell modifications. We realized, unfortunately rather late, the critical importance of the formation cycle and gas generation on cell performance of these larger multi-layer cells. Shown are 2 figures of cells with different formation cycles, either aging at room temperature or 50 degrees C. Further work to optimize the formation cycle is ongoing. The down-select LMNTO cells with optimized cell chemistry demonstrate a significant improvement in cycle life compared to both the LMNO cells and the baseline LMNTO cells without the optimized cell chemistry. This is promising and indicates that titanium substitution helps to stabilize the high voltage cathode. It also highlights the critical importance of finding a complementary electrolyte that works with the high voltage cathode. Although we were able to demonstrate meaningful improvement in cycle life, our initial 2 Ah cells did not achieve our target cycle life. Fortunately, as I will share over the next 2 slides, in parallel to this primary solid-state synthesis work, preliminary precipitation and core shell development has been completed, and the encouraging improvements in cell performance give the team confidence in the approach and achieving the project targets. This slide highlights the improvement in cell performance achieved with co-precipitation-based powders. Voltage discharge capacity curves are shown for half cells with LMNO and LMNTO cathodes made by solid-state and co-precipitation routes. The data shows trends that are also evident in full cell tests. 1. LMNO gives a higher initial capacity compared to LMNTO for both processing routes. 2. LMNTO provides better cycle life performance compared to LMNO. And 3. The initial capacity and cycle life are both improved for LMNTO and LMNO powders made by co-precipitation. Based on these results, the focus after year 1 is on precipitation-based synthesis approaches. We have also accelerated feasibility studies of the core shell cathode concept, as shown here in full cell voltage discharge capacity curves and cycling behavior. The initial core shell cathodes show improved performance compared to homogeneous solid-state cathodes. Refinement of this core shell approach with the incorporation of higher performing co-precipitation cores is a key focus of this year's work. As mentioned previously, we are very fortunate to have an excellent project team. OSU and Navitas provide invaluable expertise and capabilities to this project. Collaboration is core to Nexaris' mission, and we look forward to further collaboration as the project continues. Outside of the project team, we have had several very informative discussions with teams at Argonne, as well as other national labs, and are looking forward to opportunities to collaborate in the future to help us go further, faster. Finally, this project has enabled us to engage with automakers and other potential end users to help us better understand the value proposition of our technology and refine our T2M strategy. Future research is centered around learning from our Phase 1 foundation and continuing along our development roadmap. Key activities this year include the refinement of our precipitation and core shell synthesis processes. There will also be a continued emphasis on identifying comparable cell chemistries for the high voltage system. The recent disruptions have allowed the team an opportunity to carefully review the literature and develop strategies to better address degradation mechanisms such as gas generation and electrolyte stability. These strategies will be incorporated into our work plan going forward. In summary, we have developed a scalable solid-state process and identified a compatible cell chemistry for our titanium substituted LMNTO cathodes. 2 Ah cells with this down-select cell chemistry have been manufactured and tested, and a meaningful improvement in cycle life demonstrated compared to an LMNO baseline. The feasibility of a new core shell approach to further improve performance has been demonstrated, and precipitation processes developed for both LMNO and LMNTO powders. I would like to acknowledge the funding support from DOE Vehicles Technologies Office and invaluable guidance from our project monitor, Adrian Riggin, and the DOE led by our technology manager, Peter Fowler. Thank you for your time today, and we would like to answer any questions. Thank you.